Hey Math 135, what's up? In this video we're going to look at some problems from section 6.4 involving permutations and combinations. Number 1, there are 15 people who wish to see a movie, but the theater only has a row of 9 seats remaining. How many different ways can the theater distribute tickets? I think the intent here is that the seat that you're sitting in matters, and so from the 15 people who want to see the movie, the theater has to select 9 of those people and arrange them in seats. So this is a permutation problem. All right, there's just, again, I think of permutations as this idea of selection and arrangement. We can also think of it as there are nine things that have to be chosen without repetition. We're not going to give the same person 2 seats. All right, so we need to choose 9 things without repetition, and the order matters. Since the seat that they're sitting in matters. So this is a permutation from the 15 things available. We're picking 9 and arranging them. On the calculator, you may have to type in something that looks like 15 NPR 9, or your calculator might have a different way of entering that in. But regardless of how you get it entered in on your calculator should spit out a number that looks like 1,816,214,400. It's possible that your calculator doesn't show that many digits, and so you might see an answer in scientific notation, something that looks like 1.816 yada 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 times 10 to the, I guess that would be the 9th. Yeah, okay. 816, sorry. All right, so it might be that your calculator shows you that answer in scientific notation. Now, I suppose you could have also interpreted this as we just got to pick 9 people to go to the movie, and the seat that they're sitting in doesn't matter. Like, it's just kind of a free-for-all. All right? In which case, it might be reasonable to interpret this as just a combination problem. All right, so if you interpreted this as a combination problem, that's okay too, where we're just, from the 15 people, we're just going to pick 9 and let them fight for seats. And so when we put that into the calculator, there's only 5,005 of those. So there's a lot fewer combinations than there are permutations. But again, I think the intent for this problem is that it's a classic permutation, selection and arrangement. Number 2, a company car that has a seating capacity of 8 is to be used by 8 employees who have formed a carpool. Only 3 of the employees can drive, and we want to know how many possible seating arrangements there are for the group. Now, this is kind of like a permutation with a twist. There's only 3 people that can sit in one of the seats, and so we don't have free reign to arrange however we wish. So I think I'm going to treat this as a multiplication principle problem with 2 stages. In stage 1, I'll pick a driver, and in stage 2, we'll arrange everyone else. I guess once we pick a driver, there's 7 other passengers that we have to arrange. All right? Now, there's 3 different ways to pick a driver. There's only 3 drivers, and we got to pick one person to be the driver, so there's 3 ways to pick a driver. Arranging the other 7 is the classic permutation that we can do just by doing 7 factorial. Or I suppose if you did 7 permute 7 is another way to get the job done. All right, so we don't have a selection set where we're selecting fewer than the entire number of people available. We're just gonna take all 7 and arrange them. So that's 7 factorial. When you get this entered into the calculator, it should give you an answer of 15,120. So again, that was kind of a permutation with a twist. And I think we're going to see more of these kinds of problems than we are the classic permutation problems. It's important to be able to identify the classic permutation problem or the straight up permutation problem. These problems where we have to use the fundamental or the multiplication principle, where one of the stages is just a permutation, that's a lot more common. Moving on to number 3. We're planning a trip to California, and we want to visit Los Angeles, San Diego, Oakland, San Francisco, and Palm Springs. How many possible itineraries exist for this trip? In part A, we're going to say that we can visit the cities in any order. Okay, so this is another straight-up permutation. Of those 5 cities, we're just going to arrange those 5 cities. We're just going to arrange them. Pick all of them and pick an order for them. 5 factorial, or if you prefer the permutation notation, P 5 5 or 5 NPR 5. Same as 5 factorial. I think on the calculator it's just easier to do 5 factorial. That should give you 120 different itineraries. So if there aren't any restrictions to our itinerary, then it's just a straight up permutation. In B, we're going to visit Oakland and San Francisco consecutively. Those cities are basically right next to one another. And so if we're smart about our itinerary, we're going to visit them consecutively. In either order. Either we might go to Oakland first and then San Francisco, or San Francisco first and then Oakland. Now, there's a clever way to deal with this problem, and is to consider the Oakland, San Francisco as a group, and then each of the other stops as kind of its own. I forgot to write down LA. Each of its own stops. Okay, and so I guess one way to think about this is we gotta get on a plane. Oops, not San Francisco, Palm Springs. The idea is that we have to hop on a plane or off on a bus or something like that to get from each of the cities that are far apart to one another. But then once we're in Oakland and San Francisco, we can kind of get from one place to another by taking a taxi, or they got a subway type system there. All right, so I'm going to consider this as a 2-stage multiplication principle, where I arrange the stops or the flights or whatever you want to call it. These 4. There's four big stops. Another version of this problem is talking about going on a shopping trip, and you're visiting a certain number of stores. It just so happens that 2 of those stores are in the same mall, and so you only got to park your car once. All right, so we're going to visit those 2 stores consecutively. And so we're arranging the stops. Now there's 4 of those. That's a permutation. So 4 factorial ways to arrange those 4 stops. And then we're going to arrange the Oakland, San Francisco stop. Okay, there's 2 ways to do that. You can think of that as two ways: Oakland first and San Francisco second, or San Francisco first, Oakland second, or you can just do 2 factorial. Treat it like a permutation. I mean, both ways of thinking that are 2. 2 factorial, remember, is 2 times 1, which is also 2. All right, so in broader generality, thinking about that as its own little permutation is also good too. All right, any way that you have thinking about it, 4 factorial times 2 factorial ends up being 48. Now this idea of that's the clever idea that we maybe wouldn't expect you to come up with on your own. Although I think a lot of students, if we gave you 3 hours to figure it out, a lot of students would stumble across that. But now that you kind of seen that, you can start to think about using this idea of, hey, if we lump some of these things together in our selection set, lump some of them together, and think of like a smaller number of things in a selection set where we arrange those things and then arrange each of the individual groups. I think of this as kind of like one way to think about this maybe is permutations by group. Okay, so that's kind of a name that I gave to this kind of problem. We'll see another one later on in the examples here. Actually, part C is another one. We're going to visit Oakland and San Francisco. They either have to be the first two cities or the last two cities. Okay, the idea being, hey, if we think about it that way, then Oakland and San Francisco is a group, but then the other three cities also form a group. The other three cities also form a group, because if Oakland and San Francisco either has to be at the beginning or the end of the trip, then these other three cities are either, if Oakland and San Francisco is at the beginning of the trip, then these three cities are the end of the trip. And if Oakland and San Francisco is at the end of the trip, then these three cities are at the beginning of the trip. So now we kind of have two groups. All right, whereas before we could think of this as being four groups. Okay, so if we want to arrange the groups, well, there's two groups, so there's two factorial ways to arrange the groups. And then we have to arrange within each group. So arrange the Oakland San Francisco group. Well, there's two things in that group, so there's two factorial ways to arrange that group. And then in a third step, we'll arrange the San Diego, Los Angeles, Palm Springs group. There's three cities there, so there's three factorial ways to arrange that group. So again, I think both of these problems fall under the permutation by group banner, where we start off by arranging each of the groups. Arrange the groups as a total, and then arrange within each group. All right, so 2 factorial times 2 factorial times 3 factorial ends up being 24. Identifying, like we have these special counting problems of permutations and combinations, and if we're able to maybe identify some things that are common among other problems, we can start to recognize, hey, there's a bunch of these problems that we can kind of think of as permutation by groups. And so coming up with a good name for them, like honestly in other classes, I may have called this the itinerary problem. Hey guys, this problem looks like the itinerary problem. All right, but we'll come up with a fancier name for it. We'll call this one a permutation by group. All right, moving on to example number 4. A group of 20 males and 15 females volunteer for a medical study, and we're going to pick 5 volunteers. From those 35 people, we're going to pick 5. Part A, how many ways can the 5 subjects be selected from the 35 volunteers? So we got that selection right there. In this case, we're gonna pick 5, but there's no special arrangement for them. It doesn't matter what order we pick them in. We can just pick all 5 at the same time. Nobody's performing a special role here. All right, so this is a combination problem. From the 35 volunteers, we're going to pick 5. On the calculator, you might type in something like 35 NPR5. And you would get an answer of 324,632. All right, so that is just a straight up combination problem. In part B, we want to know how many of those selections contain at most one female. We're going to see a ton of problems with wording involving at most, at least, fewer than, more than. And one of the things that we can do in those problems is partition or write down cases. Okay? And so at most one female means either there are 0 females or there is 1 female. Okay? For 0 females, if I have 0 females, then I also need to have 5 males. All right, so I'm going to break this into a 2-stage problem where I pick my females, and then the second stage where I pick the male volunteers. Okay? And both of these we're just choosing, all right, or selecting. These are combination problems. From the females, I have 15 females to choose from. I'm going to abbreviate this: 15 choose 0. I'm not going to pick any of them. So that's not really its own step. I mean, if you do 15 choose 0 on the calculator, that just gives you 1. There's one way to choose none of them. Then for the males, we have 20 males to choose from. I'm not sure why I did the shorthand there. Probably because of space. We got to choose 5. Okay. Similarly, for the 1 female scenario, that's the other case, we have to pick 4 males to go along with that 1 female. There are 15 choose 1 ways to pick 1 female, or you can just write 15. But I think trying to understand these things, see how they're the same. If we want to see how these things work the same, we can think of all of these as a pair of combinations. Okay? One where we choose a female, one stage where we choose a female, and the second stage where we choose a male. Okay? Or choose the males. All right, so there's 20 males to choose from, and we need to pick 4 of them in this case. Okay, so these are the 2 cases, or if you want to think of partitioning this event, the at most 1 female event can be partitioned into the 0 female, 5 male case and the 1 female, 4 male case. When we type these things into our calculator, you should get 15,504 ways to pick 0 females and 5 males, and 72,675 ways to pick 1 female and 4 males. And then since this is a partition, these 2 events, these 2 sub-events are disjoint. We can just add those values together to get the total number of ways to get at most 1 female. All right, so one thing that can come into play, anytime you see at most or at least or more than or fewer than, think of writing down cases or partitioning the event. Then compute each sub-event individually and add them together at the end. So in part C, how many selections contain at least 2 females? All right, so there's some partition words. All right, if we break that down into subcases, the fewest number of females we can have is 2, and then 3 females, 4 females, 5 females. All right, so those are the 4 cases here in the at least 2 females. All right, to go along with these 2 females, we need also 3 males. The 3 females have to be paired up with 2 males, 4 females, 1 male, and 5 females, 0 males. And just as before, each of these cases we'll treat as a 2-stage multiplication principle, where we pick the females and then pick the males. So remember, we have 15 females to choose from, and in this case we need to pick 2 of those females. Of the 20 males, we need to pick 3. In the second case, from the 15 females, we need to pick 3, and then we also need to pick from the 20 males available 2 of them. In the 4 females, 1 male case, from the 15 females, we have to choose 4. And then from the 20 males, we have to choose 1. Or I guess if you realize that, hey, there's 20 ways to pick one of the males, that's fine too. And then finally, if we want all females, we have to choose, from the 15 females available, we have to choose 5 of them. And then if you want to write it down just for consistency, from the 20 males, choose none. Okay, so we could type all these in to our calculator and get numbers and then add them all up. And that would be a lot of work. That would be a lot of work. Okay, there's another thing that goes along with some of these at least, at most problems, and that's using the complement formula. Okay, so notice that in part B, we're saying that the number of females is less than or equal to 1. And in part C, the number of females is greater than or equal to 2. And in this case, that's the same. That's equivalent to saying that the number of females, not the number 4. The number of females is strictly greater than 1. Okay, notice that less than or equal to 1 and greater than 1, those are complements. Okay, those are complements. So these 2 events are complement events. If we call the at most 1 female event, if we just called that E, then this event here, the at least 2 females, is E complement. All right, we could also think of at least 2 as being the same as more than 1 female. Okay, so if we use the complement formula, the number of things in E complement, that's what we're counting here. How many things are in this event is the number of things in a universal set minus the number of things in E, and we already computed both of those values. We computed the number of things in our universal set, the number of 5-person volunteer groups in part A. That was 324,632. And then just in part B, we found the number of things in E was 88,179. And when you do the subtraction problem, it'll give you 236,453 groups have at least 2 females. Now, I would also encourage you to do these calculations too and add them up and see that they add up to 236,453. Okay? Both of these ideas here, the partition idea or the break it down into cases idea and the complement idea, they're going to be huge this semester. Okay? And you want to master these ideas as soon as you can. And kind of seeing how they're related is a really good way to kind of master those ideas. All right, let's move on to the next problem. Number 5. 25 students enter a science fair. The top 6 students are awarded 1st through 6th place trophies. How many different ways can the trophies be awarded? This ends up being a classic permutation where select 6 from 25 and then arrange. We're gonna give them 1st through 6th place trophies. So this is a permutation, right? The order matters, and we're not going to give someone 2 different trophies. Okay, so this is from 25 permute 6, or 25 and PR 6. And that number ends up being 127,512,000. Yeah, write down all those. We've seen some counting problems where they're small enough to we could actually write down the event, or sorry, the sample space in roster notation. I don't think you're writing down this sample space. You might be able to get it done if you were clever with Excel. There might be a way to get it done there, but that's a lot. That's way too many. But again, this is just a straight up permutation. Permutation of 25 taken 6 at a time. And number 6, local university. Each student is issued an identification number that contains 10 digits. The first 4 digits must be zeros, and the last digit cannot be 0. How many different ID numbers are possible? Now, in this particular problem, there's nothing in the problem statement that says that we can't repeat digits, right? In fact, the first 4 digits have to be repeated zeros. So this is not a permutation or a combination. Remember, in the permutations and combination problems, you can't have any repetition. Here, there's nothing here that's telling us that we can't repeat digits. So this is not a permutation or combination problem. It's just a multiplication principle problem. So there's 10 digits. So we'll consider this to be 10 tasks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 tasks. For the first 4 digits, they all have to be zeros. So there's only one correct way to complete the task. The last digit cannot be a 0. So there's 9 ways to do that task. And then all the other digits can be any number between 0 and 9. So there's 10 ways to choose a digit for each of those, or choose a number for each of those digits. All right, so this was kind of a trick question. This ends up being 900,000 when you get them all done. All right, number 7, how many different committees of 4 can be formed from 20 Republicans and 15 Democrats if at least one Republican and at least one Democrat must be selected? So again, we see these at least language, and that's an indicator that we might want to break these down into cases. So I got to have at least one Republican. So the fewest number of Republicans I can have is 1. If I have 1 Republican, then that means there must be 3 Democrats because there has to be 4 people on the committee. I could also have 2 Republicans and 2 Democrats. Or I could have 3 Republicans and 1 Democrat, but then that's the fewest number of Democrats that I can have. All right, so those are the 3 cases. If I want to pick 1 Republican and 1 Democrat, I can do a multiplication principle, where I choose my Republican and then choose my Democrat. Break it down into 2 stages. Choose the Republicans and choose the Democrats. For the Republicans, there's 20 Republicans to choose from, and I need to pick 1 of them. For the Democrats, there are 15 Democrats to choose from, and I got to pick 3 of them. Let's give myself maybe a little bit more space for the other cases. All right, so for the 2 Republicans, 2 Democrats case, I can do 20 choose 2 to pick my Republicans, and then 15 choose 2 to pick my Democrats. And then the last case was 3 Republicans, 1 Democrat. I could do 20 choose 3 times 15 choose 1. All right, and when you work these out on your calculator, you should get 9,100 for the 1 Republican, 3 Democrats situation. 19,950 for 2 Republicans, 2 Democrats, and 17,100 for 3 Republicans, 1 Democrat. That's a partition. These are disjoint sub-events of the at least one of each event. And so if I just add these together, we get 46,150. Okay? All right, now we have a lot of these problems. This actually looks exactly like what we did up here with these volunteers, right? The numbers are even the same. And so, all right, these problems have a similar flavor. We've also done some marble problems, I think. And so in other classes, I might refer to this as, hey, this is the marble problem, guys. But we can also think of this as combinations. Combination with groups. Just like we had permutation with groups earlier, we can have a combination with groups. We got 2 groups here. We got 2 groups, and so that's why we have a two-stage multiplication principle situation, because of the 2 groups. So this was the partition way of dealing with this. We could also think of the complement way. Okay, so if this event, if E is the set of at least one of each, the complement event, the complement would be none of one of them. Okay? At least one of each. The complement of that is like a stacked committee. That's what I'll call it. 2 M's, 2 T's, and 2 T's? Looks like it. All right. The complement event can be split into 2 cases, the 4 Republicans case or the 4 Democrats case. And I guess if you wanted to say 4 Republicans, 0 Democrats, you could do that. But let's just think about it this way. If I want 4 Republicans, I just got to pick from the Republicans. I don't even have to do anything with the Democrats. So we got 20, choose 4. If I want all Democrats, I can do 15, choose 4. So we're trying to find the number of things in our event using the complement formula, kind of rearranged. That'd be the number of things in the universal set minus the number of things in the complement. Now our universal set is that's all of the committees that can be formed. Right, the number of committees that can be formed. We have 35 politicians, and we have to choose 4 of them. So that's the total number of committees. That's our universal set, or the number of things in our universal set. And then minus the 20 choose 4 ways to have all Republicans, plus the 15 choose 4 ways to have all Democrats. All right, so if you were to type this in your calculator, you'll get the exact same answer, 46,150. Now, in this particular case, I think it's 6 of one, half a dozen of the other. There's no real benefit to doing it one way over the other. We have to do, well, I guess here's one benefit. You have to do at least, I guess maybe we could call this 20 and this 15. All right, so if we're being generous, we have to do at least 4 of these choose computations on our calculator. Here we only have to do 3 of those. And the way that we wrote this down here, we can kind of get this all done in one fell swoop on the calculator. whereas we had to kind of do some intermediate computations here. So I think the complement way is still slightly faster for thinking about doing this on a timed test. All right. Moving on to number 8, how many 4-digit odd numbers may be formed using the elements from the set 1, 2, 3, 7, 8, 9 if no elements may be used more than once? Okay, so we got no repetition here. We can't use, I have our selection set, and we're not allowed to repeat selections from that set. We had no repeats, and the order matters. All right, so this looks like a permutation, but there's a restriction here. So this is a permutation with a restriction. Now, it might seem, all right, if we only want the odd numbers, then maybe we can just find all the permutations and divide by 2, because half of the numbers should be even and half of the numbers should be odd. But in this particular selection set, more than half of the digits available are odd. In fact, 2/3 are odd. Now, I guess it might make sense that, okay, if I made numbers with these digits, that 2/3 of them should be odd. And that might be the case, but I'm not willing to take that risk. All right, so we're gonna treat this a little bit more seriously. Now, I think we could have done this with a fundamental counting principle. So I guess if we pick the last digit first, since that's the one that's got to be odd, looks like there's four ways to pick that last digit. And then we'll go ahead and pick the first digit next, and then the second digit, and then the third one, since there's no restrictions on those other than we can't repeat digits. So once I've picked my odd digit to be last, so that my number is odd, there are 5 left for the first digit, and then 4 left for the second digit. Once I've picked a last digit and a first digit, there's 4 of these elements left for the second digit, and then there'd be 3 elements left for the third digit. Now, a slightly more clever way, I don't know, maybe clever is the wrong word here. Another way of thinking that is we just deal with this restriction first. So it really is a permutation. It's a permutation with a restriction. So if we deal with this restriction first, all right, make it odd. Make it odd by choosing one of those 4 odd digits to be last, and then tack on a 3-digit number before that, which is a permutation. Permute 3 from the 5 that are remaining. So that would be 5 NPR3. So again, we're basically just saying, all right, pick an odd number, 1, 3, 7, or 9. That's going to be our last digit. And then we're just going to, from the remaining 5 element set, we're just going to tack on a 3-digit number in front of it. Okay? Either way you think about it, you should get that there are 240 numbers, 240 odd numbers that we can make from this set. Now, I'm just curious as to if we had done 2/3 times 6 NPR4. If I made a 4-digit number and then assumed, where's my calculator? There it is. And then just assumed that 2/3 of those numbers, since 2/3 of our digits were odd. So let's check that real quick to see if that line of thinking was correct. 2/3 times 6 NPR4. Hey, that actually does work out. So our intuition was correct here. So that's interesting. Now I'm still not quite sure. The intuition makes sense, and I think it works, but I'm still not 100% confident that we can do that all the time. I'd have to think a little bit harder about that. You can think about that too and see if you can come up with a good argument for why that should be true. I think my primary thing here is that if we were allowing repeats, like I'm super comfortable saying, hey, if we're allowing repeats and 2/3 of the digits available are odd, then I'm really comfortable saying that 2/3 there, 2/3 of the numbers that we can make with repeats are going to be odd. It's the fact that we're not allowed to repeat elements here that's causing me a little bit of consternation. All right, anyways, moving on to the next problem. Number 9, 12 graduate students have applied for 3 available teaching assistantships. In how many ways can these assistantships be awarded among the applicants if, in Part A, no preference is given to any one student? All right, so they're all going to get the same stipend. So once we select our, 3, we have to pick 3 of these grad students. Once we pick those 3, that's all we have to do. So this is a combination problem. 12, from the 12 graduate students, we just have to pick 3 of them. And that gives us 220 ways to award those assistantships. In Part B, it's asking how many ways are there to do it if one particular student must be awarded an assistantship. When I first saw this is a homework question, by the way. When I first saw this, I'm like, what are they getting at there? And I figured it out. Basically, we're not picking 3. One of those people has been chosen for us. Okay? We're looking at the 11 remaining students and picking 2 of them. All right? One of those 12 students, we have to pick that person. For whatever reason, they're special, and so we really only have 2 assistantships to give away to the remaining 11 students. Then 11 choose 2, ends up being 55. All right, then down to Part C. The group of applicants includes 7 men and 5 women, and it's stipulated that at least 1 woman must be awarded an assistantship. All right, so here, hopefully we've already seen a couple of examples. This is our combination with groups, or our marble problem. Okay, our group of graduate students, our selection set has been partitioned. And we have to choose some from each group. Okay? So, all right, so we have, let's call this our event, the at least 1. Number of females is greater than or equal to 1. All right, so as soon as we see the at least, we're inclined to maybe partition this. And so we could do 1 female and 2 males, or there can be 2 females and 1 male, or there can be 3 females and no males. All right, and so when we have these combinations with the group, hopefully we're catching on that we can do this in 2 stages, or one where we pick our female in this case. So from the 5 women, we have to choose 1 of them, and then from the 7 men available, we got to pick 2. All right, that ends up being 105. In the 2 females, 1 male case, there are 5 women to pick from, and we're going to pick 2 of them. And then right after that, we got a male to pick. There's 7 that we have to choose from. We got to pick 1 of them. And that works out to be 70. And then finally, for the 3 females, we've got 5 females, and then we got to choose 3 of them. That ends up being 10. And when we add these together, 105 plus 70 plus 10 gives 185. 185 different groups or ways to pick our 3 assistantships that include at least one woman. Now, notice, or maybe if you rewind, notice that when we were talking about these first 2 cases, there were 2 things that we had to do. I had to do 2 things. I had to pick a female and pick a male. And when I had to do those 2 things and they're independent, again, I'm throwing this word independent around a lot in class, but when these things are independent, it ends up being a multiplication problem. All right? So and corresponds with multiplying. And then all these ors, when we partitioned our event, I had to have 1 female and 2 males, or 2 females and 1 male, or 3 females. All the ands correspond to multiplying, and the ors corresponding to adding things up. Okay, so that's kind of a keyword way to think about the problem, but it's not nearly as good. That's kind of a fallback. If you're not quite understanding this multiplication principle business, you can kind of get some of this done by saying all the ands are multiply and all the ors are add. But I would prefer that you understand, hey, this is a two-stage multiplication principle problem. Okay? And the reason why we're adding is we've partitioned our event and computed each of the sub-events individually, and then we're going to add them all up. Okay, so that's the partition way of dealing with this at least one woman. The complement event, if we want to think about complement strategies instead, the complement would be, all right, the number of females is less than 1. That's the opposite of greater than or equal. Or I think the easier way is to say the number of females is 0. All right, how many groups contain no females? So if we wanted to know the number of things in our event, that's what we're trying to find. Our problem is to find the number of ways to pick at least one woman. The number of things in our event would be the number of things in our universal set minus the number of things in E complement. The number of ways to pick a 3-person assistantship group. We did that in part A. That was 12, choose 3. And then if we want no females, that means we have to have all males. And so from the 7 available males, we have to choose 3 from there. All right, so if you type those things into your calculator, you should also get 185. And I think, once again, the complement strategy is the easier one to execute. There are fewer things to compute. So being aware of the complement events and understanding how to compute them, again, that's a very, very important thing to be able to do. Yes, we can get it done straightforward, or the direct method, but kind of slipping through the back door instead of barging through the front door. It's a lot of times much quicker, and sometimes the only option available. So always be on the lookout for these complement, especially in the at least, at most problems. Be on the lookout for the complement and see if it's interesting. All right, last problem here. The current Colts 53-man roster consists of 8 offensive linemen, 16 offensive skill position. Those include the quarterbacks, the running backs, and the receivers, basically the people on the offense that touch the ball. There's 10 defensive linemen, 6 linebackers, 10 defensive backs, and 3 special team members. The special team is the kicker, the punter, and the long snapper. They want to build a players' leadership committee that has 1 captain and 10 assistant captains. All right, so this is almost a combination problem where we just pick 11 people to be on the leadership committee, but one of them has a special role. All right, now, there's a couple of ways of dealing with this. Okay, one way is to say, well, if I break it into a 2-stage multiplication principle, I can say pick a captain. Now there's 53 players, and we're only picking one captain, so there's 53 ways to pick a captain. And then we can pick the remaining 10. Oops. The other 10 assistant captains. Now, once I pick my captain, there's only 52 guys left on the team. So that'd be 52, and choose our 10. All right, and that works out to be, holy smokes, 838,461,283,660. So a lot of ways to pick a leadership committee. Another way of thinking about this, it's again, it's a two-stage counting multiplication principle. Sorry, I know I've been stuttering over that the entire video. In other classes, this is called the fundamental principle of counting instead of the multiplication principle. Anyways, we could pick the committee first and then choose a leader. All right, once we pick the committee, now that would be a 53 choose 11 type situation. Once we've picked our committee, though, now there's only one of those 11 people that we can take to be our captain. So that's another way of thinking about that problem. It's kind of the same idea. We just kind of rearrange the order and the numbers kind of change. But if you type that in your calculator, you should get the same answer. Just to illustrate that there's no one right way or there's no only way. It can be intimidating thinking that you have to think of the exact right way of thinking about the problem in order to get it right. No, there's other ways of thinking about the problem. All right, we want to know in part B, how many ways are there to build a players' leadership committee that consists of one special teams member and 2 players from each of the other position groups? Right, so the idea being that we kind of have some representation going on. Our players committee has some people from each of these position groups. Now, I think the best way to deal with this, now part B, there's nothing that's talking about there being a leader of the committee or a captain. So let's deal with it first. Let's just make an 11-man committee. All right. This is basically combinations by group. All right, we have 6 groups, and so there's going to be six stages in our multiplication principle. And the order in which we do these doesn't really matter. Now, I'm not going to label each of these because it would take too long, but all right, if we just go by position group, I think there's 8 offensive linemen, so we got to pick 2 offensive linemen from the 8 available. And we're just choosing them. We're not assigning them roles. We're just choosing them. We're selecting them. We're not arranging them. So that's why these are combinations. A combination by groups. All right. So that's our linemen. From the skill position, there's 16 players in the skill positions. And we got to pick 2 of them. For the defensive linemen, there's 10 defensive linemen, and we got to pick 2 of them. Same for the linebackers. There's 6 linebackers, and we got to choose 2. From the defensive backs, there's 10 defensive backs, and we got to choose 2. And then 3 special teams members, where we just have to pick 1. All right. So again, this is in earlier problems, we had to pick. We just had our selection set partitioned into 2 pieces. Here, our selection set of 53 men is partitioned into 6 pieces. And that's why we have six stages in our multiplication principle problem. All right. Now, real quick, I want you to think about, should this number be bigger than 838 billion or should it be smaller? And if you need to pause the video, pause it to think about it. And now that you've unpaused the video, there should be fewer when we were placing more restrictions on this leadership committee. And also, we're not picking a leader. Okay. So there are fewer restrictions, and we're not doing that arrangement part of picking a leader. Anyways, when we do all the calculator work, we end up with just 306,180,000. All right, and again, that's not considering that there's a one particular player who is the team captain. If we wanted to bring that into the mix, we could do something similar to what we did up here, where we pick a committee, a players' leadership committee, and then choose a captain. Well, we just found the number of ways to pick the committee. 306,180,000. And once we've picked our 11-man committee, there's again 11 ways to choose a captain. So even if we do pick that captain, there are still fewer committees. In this case, it's 3,367,980,000 compared to the 838 billion we had without these restrictions of, having a representation from each position group. Okay. At training camp, the team eats lunch together every day in the Colts cafeteria. We want to know how many ways are there for the team to line up. So we are arranging the 53 members. That is just a straight up permutation problem. So 53 factorial ways to get the job done. And if you type that into your calculator, you get a super huge number. About 4.274 times 10 to the 69, which is basically means move this decimal place 69 times and throw in a bunch of zeros. So it's a huge number. In D, we're asking how many ways are there for the players to line up for lunch. So we're still lining up for lunch in the Colts cafeteria, but they have to line up with their position group. All right, so the order matters. I guess the order mattered up here. The order matters down here, but we're also doing a permutation with the groups. So this is I just said it right there, this is a permutation by groups. This is kind of like our itinerary problem. Or permutation with groups. Okay, so we got this is going to end up being a 7-stage multiplication principle. We're going to arrange the groups. Maybe the kickers, maybe the special teams is in first, or maybe they're at the end of the line, or maybe they're somewhere in the middle. Groups. There are 6 factorial ways to arrange the groups. And then we have to arrange within each group. So for instance, we're going to arrange, let's see, what's our first group? The offensive linemen. Arrange the offensive linemen. There's 8 of them. And so there's 8 factorial ways to arrange the offensive linemen. And then we're going to arrange the skill players, again, within their group. There were 16 skill players, and so 16 factorial ways to arrange them. Let's see, what's the next group? Defensive linemen. 10 defensive linemen. So the next stage will be to arrange the defensive linemen. There's 10 of them, so there'd be 10 factorial ways to arrange the defensive linemen. Then we're arranging our linebackers. There's 6 linebackers, so 6 factorial ways to arrange the linebackers. And then we'll arrange the defensive backs. There were 10 defensive backs, and so 10 factorial ways to arrange the defensive backs. And then we have to arrange the special teams players. There were 3 of those, and so 3 factorial ways to get that job done. Now I just realized in my notes I forgot to take into consideration the special teams guys, so I got to do this again on my calculator. We got 6 factorial times 8 factorial times 16 factorial times 10 factorial got up doing this in the dark times 6 factorial times another 10 factorial and then times 3 factorial. And we get another massive number, not quite as massive as the one right before this, but this ends up being about 3.455 times 10 to the 37 on the calculator. All right, so we got some big numbers here from these permutations. They're much bigger than the combination. So this is kind of driving home the idea that, all right, if we're adding this arrangement business to what's going on, you end up with a lot more. Okay, and I guess another thing here is in these combination problems we were only doing 11, whereas here we were doing all 53 people. But yeah, the numbers can get really, really big. All right, I bet this is bigger than the number of atoms in the entire universe. Okay, all right, so that'll do it for this supplement video. If you have any questions about any of these examples, please send me a message or ask a question in class, and we'll try to get that sorted out. Also, remember, these are the kinds of questions that make Math 135 hard. And these are the kinds of questions that we're going to be working with all semester long, and the ideas that we're going to be working with all semester long. So please make the effort to get these done and to understand it as soon as you can. All right, that's all for now.